So let us talk now about time lease. We would like leaders to be disjoint in time. Here is a situation that we would like to think about. Think about a Paxos group. In a Paxos group, you have one leader and a number of followers. So at any given point of time, for example here, we would like to have only one leader. Here you can see that we have two processes, P1 and P2, and a follower Q here. Could be many followers. But at any point of time, we have one leader. In this situation, we have P1 as a leader. And here is a situation where P2 is a leader. These two leaders are disjoint in time. And if a process is a follower, so for example, Q here, so if Q is a follower, for example, of P at time t, then there are no other processes that can be leaders at time t. At any point, when a follower considers one process as a leader, so there are no other processes that are leaders. In practice, what is going to happen, as you will see, is that a follower will consider a process, for example, P1, to be a leader a little bit longer than when P1 finished his tenure as a leader. So there is a period here where P1 is not a leader, but Q is considering him as a leader. This you will see why. The same thing happens here. So Q is a follower of P2 here, but P2 is a leader only on this period. So there's a period of lag of time here that actually P2 is not a leader. So here is an outline of our solution actually, is that a proposer P that wants to become a leader sends a request, which we are now talking about a Paxos or a consensus-based algorithm, a request to the acceptors. This request is normally a prepare message. This is what happens when a process or a proposer becomes a leader for the first time. So an acceptor gives a time-based leader lease to P. So for example, the acceptor say, okay, I will accept you as a leader for 10 seconds. And if a proposer gets leases from a majority of acceptors, then this proposer will hold the lease of this group and becomes a leader. Becoming a leader is conditional on a majority of acceptor accepting him for a period of time, for example, 10 seconds. That is the lease. So in the time until the first acceptor lease expires, the proposer knows that no other proposer can hold a lease on that group. So the proposer knows he's a leader, and it cannot be the case that there are any other leader. So during this time, the leader can do any operations that do not need to change the state. For example, respond to reads from a local state. So here is the situation. P wants to become a leader. He sends a prepare message to an acceptor. The acceptor receives this message here. And in this case, he says, okay, leader, I'll give you 10 seconds to become a leader. And we will see exactly how this happens, but the leader then becomes a leader for 10 seconds. And if he wants to continue to become a leader, he has to renew the lease with the set of acceptors. Here is exactly the algorithm now. If we look to a Paxos-based, for example, sequence Paxos algorithm. Sequence Paxos algorithm would work like this. This idea of leadership can be integrated with Paxos messages. So as before, an acceptor joins round n by sending a promise, if you remember. So a leader sends a prepare, an acceptor sends a promise in what we described before. And this, of course, in response to a prepare message. What this promise normally used to do, it was a promise not to accept any proposal in lower rounds. So this we have that. But in addition, the acceptor also adds some extra promise here. So what happens is that if Q, this acceptor, joins round n at time t, then this process Q actually promises something more. It promises not to accept a higher leader or not to join a higher round. This is the same thing, not to accept a higher leader or to join a higher round until the time t plus 10 seconds. This is a new promise. And if a proposer P gets a promise from a majority, then he knows that no other proposer can get a majority of promises during this period of time. If he wants to renew the lease, he has to perform another request to renew the lease. But this is the basic idea. There's a number of issues we have to consider here. First, notice that we are only talking about physical time intervals. We are not talking about absolute clock values, because we know that we cannot absolutely synchronize clock values exactly. We're just talking about physical time. However, we have to consider two things here. We have to take into account that our network is an asynchronous, messages can take arbitrary delays, and then we have to take into account that clocks can drift apart. So these are the two things that we have to now take into consideration. Let us now consider the case with asynchronous network. So we have a process which wants to become a leader. This process P wants to become a leader at time t0. He sends a prepare message. This prepare message arrives at the follower or the acceptor at time t1. And he got a promise from himself and a promise, say, from Q. So now if we have three processes, we have now enough promises. So we got a promise from a majority. So we got this promise at T2. When the promise arrived at the acceptor Q, so Q from now on, he said, I will not accept another leader, say, for 10 seconds. So this is the case. So now we have this T4 is equal T1 plus 10 seconds. We know that very well. But what about P? How long he can be considered a leader? We have a problem here. And the problem is as follows. P does not know how long time it took for this message to arrive to Q. It could maybe take very little time, like arrive here. So the only thing that P can do is to have a conservative estimate. So again, P cannot know the exact time that Q sent the promise. It could be here or it's here. We don't know. The only thing he knows that T0 is less or equal than T1 and T1 is less or equal than T2. So from his point of view, process P has to be conservative, and he has assumed that T1 is equal to T2. And that means that P will hold the lease until T3. And T3 is, what is T3 here? Here is T3 to this point. And in this point, so T3 is T0 plus 10 seconds. So as you can see, because of the asynchronous network, the leader holds the lease shorter time than the acceptors. But that's okay. That's no problem. And the better the network, this time will be comparable, these times, or this interval will be comparable. So this is the first problem that we solved. The next one is what to do about clock drift. These clocks are not really synchronized. We're going to take care of this in the next unit.